Hello there, and welcome to 100 Space Myths that will keep you up at night. Tonight, we venture beyond the familiar boundaries of Earth, past the thin veil of atmosphere that protects us, into the vast, dark realm of space. It is a place that has captured human imagination since the first moment our ancestors looked up at the stars and wondered what lay beyond the sky. Space has become the setting for countless stories, movies, and myths, some beautiful, some terrifying, and many of them completely wrong. Perhaps your day has been filled with noise and urgency, with screens showing dramatic images of exploding spaceships and astronauts floating in zero gravity, with stories of black holes that devour everything in their path and asteroid belts so dense that navigation becomes impossible. These images are compelling, designed to thrill and frighten, but they create a version of space that exists only in fiction, not in the observable universe where physics governs all motion and matter. Tonight, you are invited to set those dramatic images aside, to rest here in the comfort of your bed, and to let the myths about space dissolve slowly, one by one, replaced by something closer to the truth, which is often stranger, more subtle, and paradoxically more comforting than the misconceptions we carry. Space is not the chaotic, hostile void that popular culture has painted it to be. It is governed by laws, predictable and patient, a realm where black holes do not hunt, where asteroid belts are mostly empty, where the sun does not burn yellow like fire. As you settle into this moment, you may notice your breathing beginning to slow, your shoulders dropping slightly away from your ears, the small muscles around your eyes softening. The day is behind you now, and the night is opening up around you like a gentle hand. Space is out there, yes, vast and dark beyond measure, but you are here, safe, held by Earth's gravity at precisely the right distance from the sun, protected by magnetic fields you cannot see but which work tirelessly to deflect harmful radiation. If you are ready, you can let your eyes close if they want to, or let them remain softly open, unfocused, gazing at nothing in particular. Let your body sink a little deeper into whatever surface supports you. The myths can wait no longer. It is time to begin setting them gently aside, one by one, making room for the quiet truth of what space actually is. Let's begin. One of the most persistent and frightening myths about space concerns black holes. Those mysterious objects that have captured popular imagination and been transformed into cosmic monsters. The myth goes like this: black holes are cosmic vacuum cleaners, powerful vortices that suck in everything around them, devouring stars and planets and anything unfortunate enough to wander nearby, pulling matter across vast distances with irresistible force. This image appears everywhere in popular culture. Movies show spaceships being dragged helplessly toward black holes from impossible distances. Documentaries describe them as insatiable cosmic predators. Science fiction uses them as convenient plot devices for disposing of unwanted objects or characters. The word suck itself appears in nearly every casual description of black holes, as though they were celestial vacuum cleaners roaming the galaxy in search of prey. But this is profoundly wrong. Black holes do not suck. They do not reach out and grab things. They do not hunt or prowl or actively pull matter toward them from great distances. What black holes do is exactly what every other massive object in the universe does. They exert gravitational force proportional to their mass and the distance between them and other objects. The confusion arises from a misunderstanding of how gravity works. Gravity is not a pulling force in the sense that a vacuum cleaner pulls. It is a warping of space-time caused by mass. Imagine space-time as a stretched rubber sheet, and massive objects as heavy balls placed on that sheet, creating depressions. Other objects roll along the sheet and either fall into the depression or orbit around it, depending on their speed and trajectory. Black holes create very deep depressions because of their extreme density, but they do not create some special sucking force that normal gravity does not have. Here is the crucial point that demolishes the myth. If the Sun was suddenly replaced by a black hole of exactly the same mass, Earth's orbit would not change at all. We would not be sucked in. We would continue orbiting at the same distance, at the same speed, following the same path we do now. We would freeze and die from lack of sunlight, certainly, but we would not spiral into the black hole. This is because the gravitational influence of an object depends on its mass and your distance from it, not on whether it happens to be a black hole. As you listen to this, you may feel a subtle shift in your understanding, a loosening of tension you did not know you were carrying. Black holes are not monsters. They are not hunting for you. They are simply very dense objects with strong gravitational fields, obeying the same laws of physics that govern everything else in the universe. You could, in theory, orbit a black hole just as safely as you orbit any other massive object, as long as you maintained sufficient distance and respected the mathematics of orbital mechanics. Astronomers have observed stars orbiting near the supermassive black hole at the center of our galaxy, completing their orbits over years or decades, never falling in because they maintain their orbital speed. These stars are not being sucked toward doom. They are simply in orbit, held by gravity, just like Earth is held in orbit around the Sun. The event horizon, the boundary beyond which nothing can escape a black hole, is certainly real and represents a point of no return. But you would have to actually cross that boundary for it to matter, and crossing it requires getting very close to the black hole or falling directly toward it. Black holes do not extend their event horizons outward to snag passing objects. The event horizon is a consequence of the black hole's gravity being so strong that escape velocity exceeds the speed of light, but this only applies to a very specific distance from the black hole center. Imagine a black hole not as a cosmic predator but as a well in space-time, sitting quietly, affecting only those objects that venture close enough to be influenced by its gravity. Most black holes are stellar mass objects formed from collapsed stars, with event horizons only a few kilometers across. Even the supermassive black holes at the centers of galaxies, millions or billions of times more massive than the Sun, have event horizons that are tiny compared to the vast distances between stars. Let that image settle over you like a soft blanket. Black holes are not vacuum cleaners. They do not suck. They simply exist, warping space around them, patient and still, following the same gravitational laws that keep the Moon orbiting Earth and Earth orbiting the Sun. Your breathing is slower now, deeper, your body relaxing into this corrected understanding. The universe is not populated by cosmic predators hunting for victims. It is populated by objects of various masses, all exerting gravity, all following mathematical laws that are strange but predictable, complex but not malicious. If sleep is beginning to approach, you can welcome it. The next myth will be waiting when you need it, but for now, let yourself rest in the knowledge that black holes, for all their strangeness and power, are not hunting for you. There is a dramatic image embedded in popular culture, repeated in countless science fiction films and television shows. The asteroid belt as a dense, chaotic field of tumbling rocks, so crowded that spacecraft must navigate carefully through narrow gaps, dodging and weaving to avoid collision, with asteroids visible in every direction, sometimes colliding with each other in spectacular crashes. This is the asteroid belt of Star Wars and other space operas, a treacherous obstacle course where piloting skill and quick reflexes mean the difference between survival and destruction. This image is so pervasive, so visually compelling, that it has become the default mental picture most people carry of the asteroid belt, that region of the solar system between Mars and Jupiter where millions of rocky bodies orbit the Sun. The myth suggests that traveling through the asteroid belt would be like navigating a minefield, requiring constant vigilance and evasive maneuvers, with danger lurking behind every rock. But the reality of the asteroid belt could not be more different. The asteroid belt is not dense. It is almost incomprehensibly empty. While it does contain millions of asteroids ranging from tiny pebbles to objects hundreds of kilometers across, these rocks are spread across such an enormous volume of space that the average distance between them is measured in millions of kilometers. If you were to fly a spacecraft through the asteroid belt, you would most likely see nothing. No asteroids tumbling past your windows, no fields of rocks requiring navigation, just the same black emptiness that characterizes most of space, with perhaps the occasional distant speck visible only through powerful telescopes. The chances of randomly colliding with an asteroid while passing through the belt are so astronomically small that NASA does not even bother to plan around them when sending spacecraft to the outer solar system. Every spacecraft we have sent beyond Mars, Pioneer, Voyager, Galileo, Cassini, New Horizons, and many others, has passed through the asteroid belt without incident, without even seeing most asteroids, because the belt is mostly empty space. When we do want to study an asteroid up close, we have to aim for it specifically, using careful navigation to intercept it, because accidentally encountering one would be like winning a lottery, possible in theory but vanishingly unlikely in practice. As you listen to this, you may feel a gentle deflation of drama, a quieting of imagined chaos. The asteroid belt is not a gauntlet to be run. It is a sparse collection of rocks drifting in the vast darkness between planetary orbits, so spread out that they are essentially invisible to each other except across enormous distances. To understand the true sparseness of the asteroid belt, consider this. If you gathered up all the asteroids in the belt and combined them into a single object, the resulting body would be smaller than our Moon. The total mass of the entire asteroid belt is only about 4% of the Moon's mass. This relatively small amount of material is distributed across a region of space shaped like a torus, a donut, with an inner radius of about 300 million kilometers and an outer radius of about 500 million kilometers. The volume of this space is so vast that the asteroids within it might as well be alone. The asteroids themselves are not careening wildly or colliding constantly. They follow stable, predictable orbits around the Sun, most of them having been in essentially the same orbits for billions of years. Collisions do happen, but they are rare events, occurring perhaps once every million years for any given asteroid, and even then usually involving smaller fragments rather than the largest bodies. Imagine the asteroid belt not as a crowded highway, but as a desert, vast and empty, with scattered rocks separated by distances so great that you could spend a lifetime traveling through it and never see two asteroids at once. The belt is defined more by emptiness than by matter, by the space between objects rather than the objects themselves. Let that image settle gently over your understanding. The asteroid belt is not a treacherous obstacle course. It is nearly empty space, populated by rocks that drift in solitude, rarely if ever encountering each other, following ancient orbits that have remained stable since the solar system's formation. Your body is sinking deeper into rest now, your breath becoming slower and more regular. The solar system is not a chaotic battlefield but an ordered system, with planets and asteroids following predictable paths, governed by gravity, stable and patient and far less dangerous than science fiction suggests. If your eyelids are growing heavy, you can let them close. The myths are being set aside, one by one, making room for a more accurate and more peaceful understanding of the cosmos. The asteroid belt is mostly empty. You could fly through it blindfolded and likely never come close to anything solid. There is a simple, unquestioned assumption that most people carry from childhood. The sun is yellow. Children draw it as a yellow circle with radiating lines. Artists paint it in shades of gold and amber. We talk about golden sunlight and describe sunny days as bathed in yellow warmth. Every illustration of the solar system shows the sun as a cheerful yellow orb, distinctly different from the white or blue stars we see at night. This myth is so deeply embedded in human culture that it seems absurd to question it. After all, you can look up on any clear day and see the sun's yellow glow for yourself, though you should never stare directly at it, of course. The evidence appears to be right there in the sky, visible and undeniable. But the sun is not yellow. The sun is white. It is classified as a G-type main sequence star, and like all stars of its type, it emits light across the entire visible spectrum roughly equally, which is what we perceive as white light. The sun appears yellow from Earth's surface only because its light must pass through our atmosphere, and that atmosphere scatters shorter wavelengths of light, blue and violet, more effectively than longer wavelengths like red, orange, and yellow. This scattering is why the sky appears blue during the day. The blue light from the sun is scattered in all directions by molecules in the atmosphere, filling the sky with diffused blue light while allowing the remaining wavelengths, weighted more toward yellow and red, to pass through more directly. The result is that when you look at the sun from Earth's surface, you see it tinted yellow or orange, especially near sunrise or sunset when the light must pass through even more atmosphere. Astronauts who have seen the sun from space, above the atmosphere, consistently describe it as white or very slightly cream-colored, not yellow. Photographs taken from space show the sun's true color, a brilliant white that contains all the colors of the rainbow in roughly equal proportion. The yellowness we associate with the sun is an artifact of our atmosphere, a filtering effect that exists only when viewed from the ground. As you listen to this, you may feel a gentle reorientation of your understanding, a small correction to an image you have carried since childhood. The sun you have drawn and imagined as yellow is actually white, and the yellow color you see is created by the air itself, by the same scattering that makes the sky blue. This correction matters because it reveals something important about observation and perception. What we see is not always what things actually are. Our atmosphere, invisible and easily forgotten, constantly modifies the light that reaches our eyes, changing colors, dimming stars, creating effects that we mistake for properties of the objects themselves rather than properties of the medium through which we observe them. The Sun's classification as a yellow dwarf star adds to the confusion, but this is a historical naming convention rather than a description of its color. The classification refers to the Sun's temperature and spectral type, not to how it appears visually. In the system astronomers use to classify stars, our Sun falls into the G-type category, which was once informally called yellow to distinguish it from hotter blue stars and cooler red stars, but this naming is somewhat misleading. In reality, the Sun's surface temperature is about 5,500 degrees Celsius, which produces light that peaks in the green-yellow part of the spectrum but includes substantial amounts of all visible colors. When these colors are combined, the result is white, not yellow. If the Sun truly emitted predominantly yellow light, everything illuminated by sunlight would appear yellow-tinted, but instead, sunlight from space reveals colors accurately because it is white light containing all wavelengths. Imagine the Sun not as the golden orb of paintings and drawings, but as a sphere of brilliant white light, so bright that it is almost painful to contemplate even in imagination. Its surface roils with convection currents, magnetic fields twist and snap, sending arcs of plasma hundreds of thousands of kilometers into space. But through it all, the light it produces is white, neutral, containing all colors equally. Let that corrected image settle gently into your understanding. The yellow Sun belongs to Earth-bound observation, filtered through miles of atmosphere. The true Sun, the Sun as it actually exists, is white. Your breathing has become very slow now, very regular, each breath requiring no thought or effort. The myths are falling away like autumn leaves, making room for more accurate understanding. The Sun is white. The sky is blue. The yellow you see is created by the atmosphere between you and the star, a beautiful artifact of light scattering that reveals the invisible air that surrounds and protects you. If sleep is drawing closer, you can welcome it. The next myth will be waiting, but for now, rest in the corrected knowledge that the Sun, like most main sequence stars of its type, shines with white light, and the yellow you have always seen is a gift from the atmosphere, painting the star in warmer tones. One of the most dramatic and terrifying myths about space appears in countless science fiction films. The idea that exposure to the vacuum of space will cause the human body to explode. The scene is familiar. An airlock opens, a character is sucked out into the void, and their body swells and bursts like an overinflated balloon, sometimes accompanied by freezing or boiling blood, eyes popping from sockets, and other graphic horrors. This image has been repeated so often that it has become accepted truth, a fact that everyone knows about space even if they have never studied physics or physiology. The myth rests on a half-truth. Human bodies are adapted to function at Earth's atmospheric pressure, approximately 14.7 pounds per square inch at sea level, and the vacuum of space offers essentially zero pressure. The reasoning goes that this pressure differential would cause the body to explode outward, unable to contain itself against the internal pressure of dissolved gases and bodily fluids. But human skin is much stronger than this myth suggests. Your skin is not a balloon. It is a tough, elastic organ designed to hold your body together under a variety of conditions, and it is more than capable of containing you even in vacuum. Animal studies and accidents involving rapid decompression have shown that skin does not rupture when exposed to vacuum. Your body would not explode. What would actually happen if you were suddenly exposed to the vacuum of space without a protective suit is certainly unpleasant, but it is not the instant, explosive death that Hollywood depicts. The most immediate problem would be the absence of oxygen. Within seconds, you would lose consciousness as your brain was deprived of oxygen. You would not be able to hold your breath. Attempting to do so would cause lung damage as the air in your lungs expanded, so the correct response would actually be to exhale. The water on your tongue and in your eyes would begin to boil, not because of heat, but because at very low pressures, water boils at lower temperatures. This would be uncomfortable and would cause swelling of soft tissues, but it would not cause you to explode. Your body would swell somewhat as dissolved gases in your blood formed bubbles, a condition similar to decompression sickness that divers experience, but again, your skin would hold. You would not freeze instantly. This is another common misconception, that the cold of space would freeze you solid in moments. But space is not cold in the way that ice or liquid nitrogen is cold. Cold is the presence of molecules moving slowly and ready to absorb heat from your body. Space is mostly empty, with very few molecules to carry heat away from you. You would eventually freeze, but it would take time. You would lose heat only through thermal radiation, a much slower process than conduction or convection. As you listen to this correction, you may feel a strange mixture of relief and continued discomfort. The vacuum of space is still hostile to human life, still immediately dangerous, but it is not the instant explosive death that you may have feared. Death would come from lack of oxygen within a minute or two, not from explosive decompression. There have been real accidents involving near vacuum exposure that confirm this more measured understanding. In 1965, a NASA technician testing a spacesuit in a vacuum chamber experienced a suit failure and was exposed to near vacuum conditions for about 14 seconds before the chamber could be repressurized. He lost consciousness but did not explode or suffer permanent injury. He reported that the last thing he remembered was the water on his tongue beginning to boil, and when he regained consciousness after repressurization, he was essentially unharmed. This is not to suggest that vacuum exposure is survivable. It certainly is not, beyond perhaps 15 to 30 seconds. But the mechanism of death is asphyxiation, not explosive decompression. Your skin is strong enough to hold you together. Your body is more resilient than Hollywood suggests, even if it cannot survive without air. Imagine yourself not as a fragile balloon ready to pop at the slightest pressure change, but as a remarkably robust organism, held together by tough, flexible skin, designed to function across a range of environmental conditions even if the vacuum of space exceeds those limits. Your body is not waiting to explode. It is held together by structures that are stronger than most people realize. Let that corrected understanding settle over you like a reassuring blanket. The vacuum of space is dangerous, yes, but not in the dramatic, explosive way that movies suggest. The danger is quieter, slower, the absence of oxygen, the loss of consciousness, but not the violent disintegration of your physical form. Your breathing is slow and steady now, your body completely at rest, protected here on Earth by the atmosphere that provides the pressure and oxygen your body needs. You are not in space. You are safe here, surrounded by air, held by gravity, with no need to fear explosive decompression because you are enclosed in the protective shell of Earth's atmosphere. If sleep is approaching, you can let it come. The myths continue to fall away, replaced by more accurate understanding that is somehow both more reassuring and more respectful of the real dangers that exist beyond our protective atmosphere. There is a common explanation for why astronauts float aboard the International Space Station. They are in space, far from Earth, where there is no gravity, or at least where gravity is so weak that it no longer affects them. This myth appears in textbooks and documentaries, repeated so often that it seems like obvious truth. The astronauts float because gravity has disappeared, leaving them in a state called zero gravity or weightlessness. But this explanation is completely wrong. Astronauts on the International Space Station are not beyond Earth's gravity. They are not in a region where gravity has disappeared or even significantly weakened. The ISS orbits at an altitude of about 400 kilometers, roughly 250 miles, above Earth's surface. At that altitude, Earth's gravitational pull is still about 90% as strong as it is on the surface. If gravity at that altitude were truly negligible, the space station would simply drift away into deep space. Instead, it remains in a stable orbit precisely because Earth's gravity is pulling on it constantly, holding it in a curved path around the planet. The astronauts float not because gravity is absent, but because they are in continuous free fall. Free fall is the key to understanding weightlessness. When you stand on Earth's surface, you feel weight because the ground pushes up against you, resisting gravity's pull. This pushing force is what you perceive as weight. When that supporting force is removed, when you jump off a diving board, for example, you briefly experience weightlessness during the fall, even though gravity is pulling on you just as strongly as before. The International Space Station and its occupants are falling toward Earth constantly, pulled by gravity. But they are also moving forward very fast, about 28,000 kilometers per hour, or roughly 17,500 miles per hour. This forward motion is so precisely balanced with the downward pull of gravity that the station falls in a curved path that matches the curvature of Earth. It is constantly falling but never getting closer to the surface because Earth curves away beneath it at the same rate. As you listen to this, you may feel your understanding of orbital mechanics shifting, pieces clicking into place. Orbit is not floating in the absence of gravity. Orbit is falling with enough sideways velocity that you keep missing the ground. The astronauts are not weightless because gravity is gone. They are weightless because nothing is pushing against them to create the sensation of weight. This distinction matters because it corrects a fundamental misconception about space and gravity. Gravity extends throughout the solar system, throughout the galaxy, throughout the universe. There is no edge where gravity stops, no boundary beyond which objects are free from gravitational influence. Even spacecraft traveling to distant planets are constantly under the gravitational influence of the Sun, Earth, the destination planet, and countless other bodies. The term zero gravity is a misnomer, though it is so commonly used that even NASA employs it for simplicity. More accurate terms are microgravity or free fall. Microgravity acknowledges that tiny gravitational forces still exist, from the mass of the space station itself, from atmospheric drag, from tidal effects, but these are so small compared to Earth's gravity that they produce only minimal effects. Imagine the space station not as floating in some gravity-free void, but as falling endlessly around Earth, tracing a circular path through space at tremendous speed, its fall perfectly balanced by its forward motion. The astronauts inside are falling too, along with the station, and because everything inside is falling at the same rate, they float relative to each other, creating the illusion of weightlessness. This is why astronauts in training practice weightlessness aboard aircraft that fly in parabolic arcs, steep climbs followed by nose dives, creating periods of free fall lasting 20 to 30 seconds. During these free fall periods, the aircraft and everyone inside it are falling together, creating the same relative weightlessness that exists on the space station, even though they are much closer to Earth's surface where gravity is even stronger. Let this corrected understanding settle gently into your mind. Astronauts float not because gravity disappears in space, but because they are falling continuously, held in orbit by the same gravitational force that keeps you pressed against your bed right now. Your body is deeply relaxed now, held by Earth's gravity, feeling the weight that astronauts temporarily escape not by leaving gravity behind, but by falling so fast and so precisely that they orbit instead of crashing. You are held. They are falling. Both of you are under gravity's influence, experiencing it in profoundly different ways. If your thoughts are drifting towards sleep, you can let them drift. The myths are being corrected one by one, and each correction brings you closer to understanding how the universe actually works, not through dramatic absence of forces, but through elegant balance of motion and gravity. There is a phrase that has become almost a cliché in science fiction and science education. In space, no one can hear you scream. This statement, made famous by the marketing for the film Alien, has become shorthand for one of space's most famous characteristics, its silence. The myth, or rather the fact that is sometimes oversimplified, is this: space is completely silent because sound cannot travel through a vacuum. This is actually true, not a myth, but it is worth understanding why it is true and what exceptions exist, because the reality is more nuanced than the simple statement suggests. Sound is a mechanical wave that requires a medium: air, water, metal, anything with molecules that can vibrate and transfer energy to neighboring molecules. Sound is literally the vibration of molecules passing energy from one to another in a chain reaction that we perceive as sound waves. Space is very nearly a perfect vacuum, meaning it contains almost no molecules. There is not enough matter in most regions of space to transmit sound waves in any meaningful way. If you were floating in space and someone screamed right next to you, you would hear nothing, even if you were close enough to touch them, because there is no air to carry the sound from the vocal cords to your ears. This is why movies that show loud explosions in space, with roaring engines and dramatic sound effects, are scientifically inaccurate. Real space is silent, profoundly, absolutely silent in a way that is almost impossible to imagine for creatures like humans who live immersed in sound. The explosions would be visible, bright flashes of light and expanding debris, but completely silent. However, the reality has subtle exceptions and complications that make it more interesting than simple silence. While sound cannot travel through the vacuum of space, it can travel through objects in space. If you were inside a spacecraft and someone knocked on the hull, you could hear it because the sound would travel through the metal of the ship. Astronauts aboard the ISS can hear each other talk because they are inside a pressurized environment filled with air. More fascinating still, astronomers have detected sound in space in an indirect way. Plasma waves, oscillations in the charged gas that exists between planets and stars, can be converted into sound waves when they encounter magnetic fields or when their frequencies are translated into the audible range. NASA has recorded these plasma waves from various spacecraft and converted them into audio files that humans can hear, creating eerie whistles, hums, and pops that reveal the electromagnetic activity of space environments. The Sun generates sound waves within its interior, massive, low-frequency oscillations caused by convection currents in its plasma. These sound waves cannot escape into space as sound, but they create detectable patterns on the Sun's surface that astronomers can observe and analyze. In a sense, the Sun rings like a bell, though the frequencies are far too low for human ears to detect even if there were a medium to carry them. As you listen to this, you may become more aware of the sounds around you right now. The ambient noise of your environment, the hum of electronics, the distant sound of traffic or wind, the subtle creaks of a building settling, sounds so constant that you usually ignore them. These sounds exist because you are surrounded by air, by atmosphere thick enough to carry vibrations. In space, all of that would disappear. The silence would be absolute, total, a quietness deeper than any you have ever experienced on Earth. Even the quietest room has some sound, the whisper of air circulation, the beating of your own heart transmitted through your bones to your ears. In space, nothing. Imagine yourself floating in that absolute silence, surrounded by the black void, watching events unfold without soundtrack, a meteor streaking past in complete quiet, a spacecraft firing its engines with brilliant light but no roar, even your own breathing inaudible because there is no air to carry the sound from your lungs to your ears. The silence of space is not peaceful in the way that a quiet room is peaceful. It is alien, absolute, the complete absence of something you have never truly been without. Let that image settle gently over you, and then let it go. You are not in that silence. You are here, on Earth, surrounded by atmosphere, by the subtle sounds of life and machinery, by the constant low hum of a planet that is never truly quiet. Your breathing is slow and deep now, and you can hear it if you pay attention. The soft sound of air moving through your nose or mouth, the faint rustle of fabric as your chest rises and falls. These sounds are gifts from the atmosphere, reminders that you are held in a cocoon of air that not only allows you to breathe but also carries sound, creates weather, burns up meteors, and does 1,000 other things you rarely notice. Space is silent, yes, completely silent in most places, but you are not there. You are here, safe in the gentle noise of a living planet, where sound carries meaning and warning and comfort, where you can hear another person's voice without needing radio equipment, where the world speaks to you constantly in whispers and shouts that space can never offer. If sleep is calling, you can answer. The silence of space is real, but it is distant, far from this room where small sounds mark the passage of time and the presence of life. There is a logical assumption that most people make about the planets in our solar system. The closer a planet is to the Sun, the hotter it must be. This reasoning seems unassailable. Proximity to a heat source should correlate directly with temperature. By this logic, Mercury, the planet closest to the Sun, orbiting at an average distance of only 58 million kilometers, should be the hottest planet in the solar system. And indeed, Mercury gets very hot. Daytime temperatures on the sun-facing side of Mercury can reach about 430 degrees Celsius, hot enough to melt lead. This extreme heat is precisely what the myth predicts. The closest planet experiences the most intense solar radiation and therefore becomes the hottest. But Mercury is not the hottest planet in the solar system. That distinction belongs to Venus, the second planet from the Sun, which orbits about 108 million kilometers from our star, nearly twice Mercury's distance. Venus is significantly farther from the Sun than Mercury, yet its surface temperature averages about 465 degrees Celsius, consistently hotter than even Mercury's hottest daytime temperatures. The reason for this apparent paradox is Venus's atmosphere. While Mercury has essentially no atmosphere to speak of, just a thin exosphere barely denser than the vacuum of space, Venus has an extremely thick atmosphere composed primarily of carbon dioxide with clouds of sulfuric acid. This dense atmosphere creates a runaway greenhouse effect, trapping heat so effectively that Venus maintains scorching temperatures day and night at the equator and poles, with almost no variation. Mercury, despite receiving more direct solar radiation, has nothing to trap that heat. During its long day, one Mercury day lasts about 59 Earth days. The sun-facing side becomes extremely hot. But during the equally long night, temperatures plummet to about -180 degrees Celsius because there is no atmosphere to retain the heat. Mercury has the most extreme temperature range of any planet in the solar system, swinging from intensely hot to brutally cold. As you listen to this correction, you may feel your understanding of planetary temperatures shifting. Distance from the Sun matters, certainly, but it is not the only factor, and sometimes not even the most important factor. Atmosphere, composition, albedo, how much light a planet reflects versus absorbs, all of these play crucial roles in determining temperature. Venus demonstrates the power of the greenhouse effect at a planetary scale. The thick carbon dioxide atmosphere allows sunlight to reach the surface but prevents infrared radiation, heat, from escaping back into space. The heat builds up, layer upon layer, until the entire planet becomes a furnace. The atmospheric pressure at Venus's surface is about 92 times that of Earth, equivalent to being almost a kilometer underwater in Earth's oceans. This makes Venus not only the hottest planet, but also one of the most hostile environments in the solar system. The combination of extreme heat, crushing pressure, and sulfuric acid clouds makes Venus far more inhospitable than Mercury, despite being farther from the Sun. Soviet probes that landed on Venus in the 1970s and 1980s survived for only minutes to a few hours before being crushed and melted by the extreme conditions. Imagine Venus not as Earth's twin, a label it sometimes receives because of similar size, but as a hellish world where lead would pool in liquid puddles on the surface, where the air is so thick it would feel more like a liquid, where the sky glows orange-red through the perpetual cloud cover, and where nothing resembling life as we know it could possibly survive. And then imagine Mercury, closer to the Sun but swinging between temperature extremes, its cratered surface baking during the long day and freezing during the long night, with no atmosphere to moderate the extremes, no weather, no sound, just the silent transition between oven and freezer. Let these corrected images settle into your understanding. The closest planet is not the hottest. Temperature is more complex than simple distance, shaped by factors that can override the obvious logic of proximity. Your body is deeply relaxed now, resting at a comfortable temperature maintained by Earth's atmosphere, which is thick enough to create weather and moderate temperature, but not so thick as to trap heat the way Venus's atmosphere does. Earth exists in a balanced state, neither too hot nor too cold, with an atmosphere that is neither too thin like Mercury's nor too thick like Venus's. This balance is not an accident, but the result of Earth's specific distance from the Sun, its mass, its magnetic field, its water, and countless other factors that have combined to create conditions where life can flourish. You are held within this balanced system, protected from the temperature extremes that other planets experience, kept at temperatures that allow water to exist as liquid, that allow your body to function without extraordinary adaptation. If sleep is drawing near, you can welcome it. The myths continue to fall away, replaced by more complex and more accurate understanding of how planets work, how temperature is determined by more than simple proximity, how atmosphere can transform a world from merely hot to utterly hellish. When people think of Mars, they picture a red planet, glowing in the night sky with a distinct rusty hue. This redness is real, visible even to the naked eye, and it has captured human imagination for millennia. Ancient civilizations associated Mars with fire and war, with blood and heat, because of its red color. The myth that persists, often unconsciously, is that Mars is red because it is hot, that the color indicates heat the way glowing coals in a fire glow red. But Mars is not hot. Mars is actually quite cold, far colder than Earth and colder than its appearance might suggest. Average temperatures on Mars hover around -60 degrees Celsius, with winter temperatures at the poles dropping below -125 degrees Celsius. Even on the warmest summer days near the equator, temperatures might briefly reach about 20 degrees Celsius, comfortable by Earth standards, but the average remains well below freezing. The redness of Mars has nothing to do with temperature. Mars is red because its surface is covered in iron oxide, rust. The planet's soil contains large amounts of iron that has oxidized over billions of years, creating the characteristic red-orange color that covers much of the planet's surface. Mars is essentially a rusty world, and that rust is what gives it its distinctive color. The process that created this rust happened long ago, when Mars had a thicker atmosphere and possibly liquid water on its surface. The iron in the Martian rocks reacted with oxygen, either from water or from the atmosphere, gradually oxidizing and spreading across the surface as dust. Today, this iron-rich dust covers much of Mars, blown around by winds that can create planet-wide dust storms. As you listen to this correction, you may feel another small assumption being gently dissolved. Color does not indicate temperature except in specific contexts, like heated metal or stars, where the relationship between color and temperature follows predictable physical laws. But a planet's surface color tells you about its composition, not its temperature. Mars could be blue like Earth and still be just as cold. Earth could be red like Mars and still be just as warm. The color of a planet's surface depends on what materials are present and how they reflect light, not on how hot or cold those materials are. This misconception about Mars extends to other aspects of the planet as well. Because Mars appears warm-colored and is often described as Earth-like, people sometimes imagine it as a desert world similar to Earth's warm deserts, hot, dry, but not impossibly hostile. In reality, Mars is more like Antarctica than the Sahara, a frozen desert where the thin atmosphere provides almost no insulation and temperatures rarely rise above freezing. The Martian atmosphere is about 1% as thick as Earth's, composed mostly of carbon dioxide, and provides minimal greenhouse warming. Without a thick atmosphere to trap heat, Mars loses warmth rapidly. The thin atmosphere also means that even when temperatures do rise slightly during the day, the air feels colder than the thermometer suggests because there is so little air to carry heat. Imagine standing on Mars, surrounded by red-orange landscape that stretches to the horizon under a butterscotch sky. The color might suggest warmth, but you would be freezing, the cold seeping through any spacesuit, your breath, if you were somehow breathing the thin atmosphere, forming crystals instantly. The red dust would blow past you in the weak winds, and you would understand viscerally that color and temperature have no necessary connection, that Mars is red not because it is hot, but because it is rusted, a cold, oxidized world where iron has given up electrons over billions of years. Let that image settle and then release it. Mars is red and cold. Color does not indicate temperature. The association between the two exists in human perception and cultural interpretation, but not in physical law. Your body is warm now, maintaining its temperature through metabolism, wrapped in blankets or clothing, resting in a room kept comfortable by Earth's atmosphere and perhaps by heating systems designed to compensate when that atmosphere is not warm enough. You are not on Mars. You are here, on a blue planet that is warm enough for liquid water, where the air is thick enough to breathe and to hold heat, where the colors around you, whatever they may be, tell you nothing reliable about temperature because you have evolved to maintain your own warmth independent of your surroundings. If your thoughts are drifting towards sleep, let them drift. The myths are being corrected gently, without urgency, making room for more accurate understanding that sometimes contradicts intuition, that sometimes separates things, like color and temperature, that seem connected but are actually independent. One of the most persistent and proudly repeated claims about human achievement is that the Great Wall of China is the only man-made structure visible from space, or at least visible from the moon. This myth appears in textbooks, tour guides, and general knowledge, a fact that everyone seems to know, a source of pride in human engineering. The Great Wall, stretching thousands of kilometers across China, built over centuries, surely must be visible from the great distances of space. But this is false. The Great Wall of China is not visible from space with the naked eye, and it is certainly not visible from the moon. Astronauts who have orbited Earth have confirmed this repeatedly. The Great Wall is too narrow and too similar in color to the surrounding landscape to be distinguished from low Earth orbit, let alone from lunar distances. The myth likely originated before humans had actually gone to space, when people speculated about what would be visible from orbit based on the wall's length without considering its width. The Great Wall is indeed very long, about 21,000 kilometers when all of its branches and sections are included, but it is also very narrow, averaging about 6 to 7 meters wide. From the International Space Station's orbit of about 400 kilometers altitude, this is far too narrow to see without optical aid. To put this in perspective, imagine looking at a human hair from a distance of about 2.5 kilometers. That is roughly the equivalent angular size of the Great Wall as seen from low Earth orbit. Without binoculars or a camera with a zoom lens, you would have no chance of seeing it. Astronauts can see many things from space: cities at night, their lights blazing in the darkness, the geometric patterns of agricultural land, large highways and airports, rivers and coastlines, deforestation and environmental changes. But individual structures, even very long ones, are generally too small to see unless they are exceptionally bright or contrasting with their surroundings. Some astronauts have claimed to see the Great Wall under perfect conditions with perfect lighting, but these claims are disputed and likely involve other structures being mistaken for the wall, or the use of camera zoom rather than naked eye observation. The consensus among most astronauts and space agencies is clear. The Great Wall is not readily visible from space and is certainly not the only or the most visible human structure. As you listen to this correction, you may feel a small deflation of a cherished fact, something you may have repeated to others or been taught in school. The Great Wall is still an extraordinary achievement, still a testament to human determination and engineering, but it does not have the distinction of space visibility that myth has granted it. From the Moon, about 384,000 kilometers away, Earth itself is small, appearing roughly the size of a quarter held at arm's length. At that distance, no human structures are visible at all. Continents are visible, oceans, ice caps, major weather patterns, but no buildings, no walls, no cities. The claim that the Great Wall is visible from the Moon is completely false. Interestingly, while the Great Wall is not visible from space, there are many other signs of human activity that are clearly visible. The sprawling networks of cities create visible light pollution at night. Large-scale agriculture creates geometric patterns visible during the day. Major highways form visible lines. Deforestation and desertification are clearly observable. In some ways, humanity's impact on Earth is very visible from space, just not in the form of individual structures like walls. Imagine looking down at Earth from orbit, seeing the planet as astronauts do, a beautiful blue sphere wrapped in swirling white clouds, with brown and green continents and the deep blue of oceans. You can see the Sahara Desert, vast and tan. You can see the Amazon rainforest, a dark green expanse. You can see snow-covered mountain ranges and long coastlines where land meets sea. At night, you see the blazing lights of cities, creating golden webs across the continents. But individual structures, even very long walls, disappear into the complexity of the landscape, too small to distinguish. Let that corrected image settle into your understanding. The Great Wall of China is not visible from space. Human impact on the planet is visible in other ways, in our lights, our cities, our alteration of landscapes, but not in individual architectural achievements. Your body is very relaxed now, sinking deeper into rest. The myths are being corrected without drama, without the need for you to memorize or remember, just gently making room for more accurate understanding of what space observation actually reveals. If sleep is very close now, you can welcome it. The Great Wall remains on Earth, impressive when you walk along it but invisible from orbit, a reminder that human achievements are best appreciated at human scales, from ground level where we can see the detail and effort that goes into building something that endures. When we imagine a meteorite falling from space and striking the ground, the image is often dramatic. A blazing streak of fire across the sky, a glowing rock that slams into the Earth still red-hot from its passage through the atmosphere, so hot that it burns the ground where it lands, so hot that anyone touching it would be instantly burned. This image appears in movies and science fiction, and it aligns with our intuition about friction. The meteorite is moving incredibly fast through the atmosphere. Friction generates enormous heat. Therefore, the meteorite must be scorching hot when it lands. But this is mostly wrong. While it is true that meteorites experience extreme heating during their passage through the atmosphere, by the time they land, most meteorites are not hot. In fact, they are often cold or at most room temperature. The heating that occurs during atmospheric entry affects only the outer surface of the meteorite, and it happens during the brief period when the object is moving through the upper atmosphere at hypersonic speeds. This surface heating creates the visible media, the streak of light we call a shooting star, as the outer layers of the rock vaporize and ionize the surrounding air. But this heating phase lasts only a few seconds. As the meteorite descends and encounters thicker air, it slows down rapidly. Most meteorites have lost so much speed by the time they reach the lower atmosphere that they are no longer experiencing significant frictional heating. For the last several kilometers of descent, the meteorite is in free fall at terminal velocity, the speed at which air resistance balances gravitational acceleration, which for a typical meteorite is only about 200 to 400 kilometers per hour, fast enough to be dangerous if it hits something but not fast enough to generate significant heating. During this terminal velocity phase, which can last 30 seconds to several minutes depending on the altitude at which the meteorite slowed to terminal velocity, the object is passing through cold high-altitude air. This cold air cools the meteorite rapidly, removing the heat from its surface. The interior of the meteorite, which was never heated because heat does not have time to conduct inward during the brief hypersonic phase, remains at the temperature of space, which is very cold. As you listen to this, you may feel your intuitions about meteorite shifting. The dramatic burning rock that you imagined landing with a sizzle is replaced by a more subtle reality, a rock that was briefly very hot on its surface, but which cooled during its descent and lands warm at most, sometimes even cold enough to form frost on its surface from atmospheric moisture. There are documented cases of meteorites being found with frost on them shortly after landing. Witnesses who have touched freshly fallen meteorites report that they are cool or at most slightly warm, not burning hot. The outer surface may show signs of melting, a glassy fusion crust that formed during the hypersonic phase, but this is not currently hot. It is simply evidence of past heating. This correction matters because it affects how we search for and handle meteorites. You do not need to wait for a meteorite to cool before touching it. You do not need heat-resistant gloves. The danger from a meteorite is not heat but impact. If it hits you directly during its fall, the kinetic energy could be fatal, but once it has landed, it is simply a rock, no hotter than the surrounding environment. There are exceptions, of course. Very large meteorites, more accurately called bolides when they are large enough to create significant explosions, can retain more heat and may be warm or hot when they land because their greater mass retains heat longer. But typical meteorites, ranging from pebble-sized to football-sized, are cool by the time they reach the ground. Imagine a meteorite's journey. It begins as part of an asteroid or comet in the cold vacuum of space, where temperatures hover near absolute zero. It breaks free, perhaps from a collision, and drifts through space for millions of years at that same cold temperature. Then it encounters Earth, plunging into the atmosphere at perhaps 20 kilometers per second. For a few seconds, its surface becomes incandescent, glowing white-hot, ablating away in a spectacular display. But then it slows, the heating stops, and the cold high-altitude air begins cooling it rapidly. By the time it reaches the ground, it is just a cold rock with a melted crust, still carrying the chill of space in its interior. Let that corrected understanding settle gently. Meteorites are not hot when they land. The fire you see streaking across the sky is not the meteorite itself, but the ionized air around it, the heat of atmospheric compression and friction affecting only the outermost layer for only a few seconds. Your body is completely relaxed now, warm and comfortable in your bed, not needing to worry about burning rocks falling from the sky. The meteorites that land on Earth each day, and several dozen do, though most land in oceans or uninhabited areas, are simply rocks, cold from their journey through space, briefly warmed by their passage through air, but cool again by the time they rest on the ground. If sleep is very near now, you can let it come. The myths continue to dissolve, making room for understanding that is more accurate and often more surprising than the dramatic versions we learned from movies and stories. Saturn is the jewel of the solar system, famous for its spectacular ring system that makes it instantly recognizable in photographs and through telescopes. These rings are wide, bright, and beautifully structured, visible even through small amateur telescopes from Earth. For centuries, Saturn was thought to be unique in possessing rings, and even today, many people believe that Saturn is the only ringed planet in our solar system. But this is false. Saturn is not the only planet with rings. All 4 of the giant planets have ring systems. Jupiter, Uranus, and Neptune all have rings, though these rings are much fainter and less extensive than Saturn's magnificent system. Jupiter's rings were discovered in 1979 by the Voyager 1 spacecraft and were a complete surprise to astronomers. These rings are thin and faint, composed mostly of dust particles rather than the larger ice chunks that make up Saturn's rings. Jupiter's rings are so faint that they are invisible from Earth with ordinary telescopes and can only be seen in images taken by spacecraft or by the most powerful Earth-based telescopes under specific conditions. Uranus has a ring system discovered in 1977 when astronomers observed the planet passing in front of a distant star and noticed that the star's light dimmed slightly several times before and after the planet itself blocked the star. This pattern indicated rings surrounding the planet. Uranus's rings are narrow and dark, made of material that reflects very little light, quite different from Saturn's bright, icy rings. Neptune's rings were confirmed in 1989 by Voyager 2, though astronomers had suspected their existence based on stellar occultation observations similar to those that revealed Uranus's rings. Neptune's rings are faint and dusty, with some showing strange arc structures where the material is concentrated in certain sections rather than being evenly distributed. As you listen to this, you may feel your mental image of the solar system being updated. Saturn is no longer uniquely special in having rings, though its rings remain by far the most impressive, the most visible, and the most beautiful. Why does Saturn have such spectacular rings while the other giant planets have only faint, dusty rings? The answer likely involves a combination of factors. The composition of Saturn's rings, mostly water ice, which is highly reflective, and their size and mass, which are much greater than the ring systems of the other planets. Saturn's rings may be relatively young in astronomical terms, possibly only a few 100 million years old, formed from the breakup of a moon or a captured comet. The rings of the other planets may be older and more degraded, or they may have formed differently from dust generated by impacts on small moons. Even some moons in the solar system have rings or ring-like structures. Scientists have discovered that some asteroids also have ring systems, tiny and faint but real. Rings appear to be more common in the universe than we once thought, not unique to Saturn but present wherever the right conditions exist. A planet or large body with sufficient gravity, a source of ring material such as a destroyed moon or captured debris, and orbital dynamics that allow the rings to remain stable for long periods. Imagine the solar system not with one ringed planet standing out as unique, but with 4 giant planets all wearing rings, each system different in character. Jupiter's rings are dusty and faint, barely visible. Uranus's rings are narrow and dark, like thin black bands. Neptune's rings are patchy and incomplete, with bright arcs breaking up the symmetry. And Saturn's rings are wide, bright, and impossibly beautiful, structured into thousands of narrow ringlets separated by gaps, tilted at various angles to our view so that sometimes we see them nearly edge-on and sometimes we see them wide open, displaying their full glory. Let that more complete picture settle into your understanding. Saturn is not unique in having rings, but its rings are uniquely spectacular, which is why they captured human attention first and remain the iconic image of a ringed world. Your breathing is very slow now, very deep, your body completely at rest. The solar system is more complex than the simple pictures in children's books suggest, with features that are more common than we once thought, with beauty distributed across multiple worlds rather than concentrated in just one. If sleep is pulling you downward now, you can let it pull. The rings of Saturn will still be there tomorrow, along with the fainter rings of the other giant planets, all of them circling their worlds in the silent darkness, patient and enduring, whether we see them or not. There is a phrase that has entered popular culture so completely that a major rock album bears its name: the dark side of the moon. This phrase refers to the hemisphere of the moon that is never visible from Earth, the far side that remained unknown until spacecraft orbited the moon and photographed it for the first time in 1959. The myth suggests that this hidden hemisphere is perpetually dark, never receiving sunlight, locked in eternal night. But this is completely wrong. There is no dark side of the moon in the sense of a hemisphere that never sees the sun. Every part of the moon experiences day and night, sunlight and darkness, as the moon rotates on its axis. The correct term for the hidden hemisphere is the far side of the moon, not the dark side. The confusion arises from the moon's synchronous rotation, also called tidal locking. The moon rotates on its axis at exactly the same rate that it orbits Earth, taking about 27.3 days for both one rotation and one orbit. This synchronization means that the same side of the moon always faces Earth, and the opposite side always faces away. From Earth, we never see the far side. It is permanently hidden from our view. But hidden from Earth's view is not the same as never receiving sunlight. As the moon orbits Earth, different parts of it are illuminated by the sun. During a new moon, when the moon is between Earth and the sun, the far side is fully illuminated while the near side, the side we see, is dark. During a full moon, the near side is fully illuminated and the far side is dark. Both sides experience approximately equal amounts of sunlight over the course of a lunar month. Imagine standing on the far side of the moon. The sun rises and sets just as it does on the near side, though the day-night cycle lasts about 29.5 Earth days, almost 2 weeks of continuous sunlight followed by almost 2 weeks of darkness. You would never see Earth. It would be permanently below your horizon, hidden just as the far side of the moon is hidden from Earth, but you would see the sun, the stars, and all the same celestial objects that someone on the near side would see, just at different times. As you listen to this, another small misconception dissolves. The dark side of the moon is not dark except during full moons, when the side facing away from Earth is also facing away from the sun. The rest of the time, the far side receives just as much sunlight as the near side. The phrase dark side of the moon probably persists because dark can mean both unlit and unknown. The far side was certainly unknown before space exploration. It was mysterious, unexplored, inaccessible to observation. In that sense, it was dark to human knowledge even though it was physically illuminated half the time. When Soviet spacecraft finally photographed the far side in 1959, scientists discovered that it looks notably different from the near side. The far side has almost no large dark areas, no Maria, the smooth basaltic plains that create the face we see when looking at the full moon. Instead, the far side is heavily cratered and mountainous, covered in ancient highlands. This difference likely relates to the moon's internal structure and the fact that the near side faced Earth during a period of heavy volcanism that filled many of the impact basins with lava. Let the corrected understanding settle gently. Both sides of the moon receive sunlight. Both sides experience day and night. The moon is not divided into a light side and a dark side, but into a near side and a far side based on what is visible from Earth. Your body is very relaxed now, sinking deeper into the comfort of your bed. The moon above, whether you can see it tonight or not, is slowly rotating, slowly orbiting, showing different faces to the sun while always showing the same face to Earth, a celestial dance that has continued for billions of years and will continue for billions more. If sleep is very close, you can welcome it. The moon has no permanently dark side, just as most myths about space dissolve when examined carefully, replaced by realities that are often more interesting and more subtle than the simplified stories we first learned. This myth is not exclusively about space, but it relates to atmospheric phenomena and the relationship between Earth and the electrical activity of its atmosphere, so it belongs in our collection. The saying is familiar to everyone: lightning never strikes the same place twice. This phrase has become a metaphor for rare events, suggesting that if something improbable has already happened once in a particular location, it will not happen again. But this is demonstrably false. Lightning strikes the same place repeatedly, especially if that place is tall, pointed, or otherwise conducive to electrical discharge. The Empire State Building in New York is struck by lightning approximately 20 to 25 times per year. Tall towers, mountaintops, and trees in open fields are struck repeatedly because they are the easiest paths for electrical charge to travel between cloud and ground. Lightning is an electrical discharge that occurs when the difference in electrical charge between a cloud and the ground, or between different parts of a cloud, becomes large enough to overcome the insulating properties of air. The lightning follows the path of least resistance, which typically means traveling through or near tall objects that reduce the distance the charge must travel through air. There is nothing about a previous lightning strike that would prevent another strike from occurring in the same location. Each lightning event is independent, responding only to the current distribution of electrical charge in the atmosphere and the conductivity of potential paths. If conditions are right for a strike, and a particular location offers the best path, lightning will strike there regardless of whether it has struck there before. As you listen to this correction, you may be mentally reviewing other myths and folk wisdom, wondering what other commonly repeated sayings are similarly inaccurate. The phrase "lightning never strikes twice" may have originated as an attempt to provide comfort or reassurance, suggesting that someone who has already experienced a rare misfortune need not fear it happening again. There is a comforting assumption about the night sky, that the North Star, Polaris, has always guided navigators throughout human history, that it has been the fixed point around which the heavens turn since ancient times, unchanging and reliable. Polaris sits almost directly above Earth's North Pole, making it appear stationary while all other stars wheel around it as Earth rotates. This stability seems eternal, a permanent feature of the cosmos. But Polaris has not always been the North Star, and it will not always be the North Star in the future. The position of Earth's rotational axis changes slowly over time in a motion called precession, similar to how a spinning top wobbles as it slows down. This axial precession means that the point in the sky directly above Earth's North Pole traces a slow circle through the stars, taking approximately 26,000 years to complete one full cycle. Currently, Polaris happens to be very close to the North Celestial Pole, within about 1 degree, making it an excellent navigation reference. But 5,000 years ago, when the ancient Egyptians were building the pyramids, the star Thuban in the constellation Draco was closer to the North Celestial Pole and served as the North Star. In about 12,000 years, the bright star Vega will be the North Star, and in another 14,000 years after that, the cycle will bring the pole back near Polaris again. This precession is caused primarily by the gravitational influence of the Moon and Sun on Earth's equatorial bulge, the slight thickening of Earth around its middle due to rotational forces. These gravitational tugs create a torque that slowly changes the orientation of Earth's axis. The effect is tiny from moment to moment, shifting the celestial pole by only about 50 arcseconds per year, but over centuries and millennia, the movement becomes significant. As you listen to this, you may feel your sense of celestial permanence shifting slightly. Even the North Star, that symbol of constancy and reliability, is temporary in its role, an accident of timing that placed Polaris near the North Celestial Pole during the current era of human civilization. Ancient navigators and astronomers were aware that the sky was slowly changing. Greek astronomer Hipparchus discovered precession around 150 BCE by comparing his own observations of star positions with records made by earlier astronomers and noting small but systematic differences. He realized that the entire coordinate system of the sky was slowly rotating, though the cause would not be understood until Newton explained it through gravitational mechanics. This precession also affects the timing of the seasons relative to Earth's orbit. The concept of the Age of Aquarius in astrology refers to precession moving the vernal equinox, the point where the Sun crosses the celestial equator in spring, from one zodiac constellation to another. These ages last about 2,160 years each as the equinox point precesses backward through the zodiac. Imagine the night sky not as a fixed dome but as a slowly rotating projection, the stars maintaining their relationships to each other, but the entire pattern shifting gradually relative to Earth's poles and equator. Over human lifetimes, this motion is imperceptible without careful measurement, but over the span of civilizations, the sky rearranges itself, different stars taking turns at the celestial pole, the constellations of the zodiac shifting relative to the seasons. Let that image settle into your understanding. Polaris is the North Star now, but it is a temporary arrangement, a cosmic coincidence that happens to be useful for current human navigation. In the deep past and the distant future, other stars take that role, and Polaris becomes just another star in the constellation Ursa Minor, no longer special, no longer the pivot point of the northern sky. Your body is deeply relaxed now. You're breathing slow and effortless. The stars above are moving in ways too slow for human perception but real nonetheless, participating in cycles that span thousands of years, reminding us that even celestial navigation markers are temporary, that constancy at human timescales can be changed at cosmic timescales. If sleep is very close now, you can let yourself drift toward it. The North Star will still be there tomorrow night, still near the pole, still useful, but now you know it is a temporary guide, holding its position for a few more thousand years before yielding to Vega, to other stars, in the endless slow wobble of Earth's axis. This myth connects Earth's oceans to the broader theme of exploration and the unknown. Many people assume that in the age of satellite imagery and advanced technology, we have thoroughly explored and mapped Earth's oceans, that the ocean floor is known and catalogued much like Earth's land surfaces. After all, we have sent robots to Mars, spacecraft to the outer solar system. Surely we have explored our own oceans. But this assumption is dramatically wrong. We have better maps of the surface of Mars than we have of our own ocean floor. More than 80% of the ocean remains unmapped, unobserved, and unexplored by humans. The deep ocean is one of the least known environments on Earth, holding mysteries that rival anything in space. The ocean covers about 71% of Earth's surface, and its average depth is about 3,800 meters, more than 2 miles. The deepest parts, the ocean trenches, reach depths of nearly 11,000 meters in places like the Mariana Trench. These depths are extremely difficult and expensive to explore. Water pressure increases by 1 atmosphere, about 14.7 pounds per square inch, for every 10 meters of depth. At the bottom of the Mariana Trench, the pressure is over 1,000 times greater than at the surface, enough to crush most submersibles like tin cans. Only a handful of humans have ever visited the deepest parts of the ocean, fewer than have walked on the moon. The first crewed descent to the bottom of the Mariana Trench occurred in 1960, and only a few expeditions have returned since. In contrast, 12 humans walked on the moon between 1969 and 1972. The technology required for deep ocean exploration is in some ways more challenging than space exploration. Spacecraft must withstand vacuum and radiation, but deep-sea vehicles must withstand crushing pressure and complete darkness. Communication is difficult because radio waves do not propagate well through water. Navigation is challenging because GPS signals cannot penetrate seawater. As you listen to this, you may feel a shift in perspective about what remains unknown. We often imagine that the great age of exploration is over, that Earth has been thoroughly mapped and catalogued, with only space remaining as the final frontier. But vast regions of our own planet remain as mysterious as distant moons, as unexplored as the surfaces of other planets. The deep ocean contains creatures and ecosystems that seem as alien as anything we might find on another world. Organisms that have never seen sunlight, that live under crushing pressure, that survive near volcanic vents where water reaches temperatures above boiling but remains liquid due to pressure. Bioluminescent creatures that create their own light in the total darkness. Species that have evolved in complete isolation, unknown to science until accidentally discovered by research submarines. Recent deep-sea expeditions continue to discover new species at a remarkable rate, suggesting that the ocean holds perhaps millions of species that have never been catalogued. Each exploration of a new deep-sea region reveals ecosystems and organisms that challenge our understanding of life's possibilities. Imagine the ocean floor stretching beneath you, dark and unexplored, holding canyons deeper than mountains are tall, plains wider than continents, volcanic ranges that dwarf anything on land, all of it hidden beneath miles of water, mapped only in the coarsest detail, known mostly through indirect measurements rather than direct observation. While we send robots to Mars and probes to the outer solar system, vast regions of Earth's own surface remain unvisited, their secrets kept by depth and pressure and darkness. Let that humbling realization settle gently. Earth itself is not fully known. The ocean keeps its secrets, revealing them slowly, reminding us that exploration and discovery are not finished, that mysteries remain even on the world where we evolved. Your breathing is very slow now, very deep, your body at rest on land, far from the ocean depths. You are safe here, at atmospheric pressure, in air rather than water, with light and warmth and gravity that feels normal. The ocean depths are distant, separate from you, but they are there, vast and mostly unexplored, holding wonders and terrors that we are only beginning to glimpse. If sleep is pulling you down now like deep water, you can let it pull. The myths are almost all corrected now, making room for more accurate understanding of what is known and what remains unknown, both in space and on Earth. One of the most common and innocent misunderstandings about the night sky concerns those brief streaks of light that flash across the darkness, shooting stars. The name itself perpetuates the myth. These are not stars at all, yet we call them shooting stars and make wishes on them, treating them as special celestial events involving actual stars. Many people, especially children, imagine that these are distant stars moving rapidly across space or perhaps falling from their positions in the sky. But shooting stars are not stars. They are meteors, small pieces of rock or ice, usually no larger than a grain of sand, that enter Earth's atmosphere at high speed and burn up due to friction and compression heating. The streak of light you see is not the object itself, but the superheated air around it as it plummets through the atmosphere at speeds ranging from 11 to 72 kilometers per second. Most meteors come from comets. As comets orbit the sun, they leave trails of debris, dust and small rocks shed from the comet's surface as it is heated. When Earth's orbit intersects one of these debris trails, the particles enter our atmosphere and create meteor showers, periods when numerous shooting stars appear to radiate from a single point in the sky. Individual sporadic meteors can occur any night, caused by random debris in space encountering Earth. But meteor showers are predictable, occurring at the same time each year as Earth passes through the same debris trails. The Perseids in August, the Leonids in November, the Geminids in December. These are annual meteor showers, each associated with a specific comet or, in some cases, an asteroid. The particles themselves are tiny. A typical shooting star is created by a particle about the size of a grain of sand weighing less than a gram. Brighter meteors, called fireballs or bolides, are created by larger objects, perhaps pebble-sized or larger, but even these are nothing compared to the scale of actual stars. As you listen to this, the name shooting star may seem more obviously metaphorical. These are not stars falling from the sky, but tiny bits of ancient comets and asteroids meeting their end in Earth's atmosphere, creating brief flashes of light that last only a second or two before disappearing completely. Real stars are incomparably larger and more distant. The nearest star other than the Sun is Proxima Centauri, about 4.2 light-years away. Even if a star were somehow moving toward Earth at an appreciable fraction of the speed of light, which none are, it would take years to show any noticeable change in position. Stars do not zip across the sky in seconds. They maintain their positions relative to each other over human lifetimes and even over centuries, moving only slowly through proper motion that requires precise measurement to detect. When a star truly dies, if it is massive enough, it explodes in a supernova, an event so energetic that for a brief time, the dying star can outshine its entire galaxy. But this happens in distant space, often thousands or millions of light-years away, and what we see is simply a new bright point appearing in the sky, not a streak of motion. Supernovae do not shoot across the sky. They appear, brighten, and then fade over weeks or months. Imagine yourself lying on your back on a clear dark night, watching the sky. The stars above are fixed, moving only with the slow rotation of Earth, maintaining their patterns. Then a streak appears, a brief line of light cutting across your field of view, gone in a second. That was not a star. That was a tiny piece of debris, perhaps older than human civilization, perhaps shed from a comet that last visited the inner solar system centuries ago, ending its journey in a brief flash of light as it vaporized in Earth's atmosphere. Let that corrected image settle into your understanding. Shooting stars are meteors, tiny visitors from space that burn up harmlessly in the atmosphere, creating beautiful light shows but having nothing to do with actual stars. Your body is completely relaxed now, heavy and still. You're breathing slow and even. Above you, whether you can see them or not, real stars continue their patient existence, burning through nuclear fusion, aging over billions of years, far too distant and too massive to ever shoot across your sky. If sleep is very near, you can welcome it. The next time you see a shooting star, you can know what it truly is. Not a star at all, but a cosmic pebble meeting Earth's atmosphere, a tiny messenger from the solar system's ancient past, beautiful in its destruction, brief in its brilliance, and completely harmless to you safe here on the ground. And so we come to the end of this long, gentle journey through 100 myths that humans tell about space. You have drifted through misconceptions about black holes that supposedly devour everything nearby, about asteroid belts imagined as dense obstacle courses, about the color of the sun and the nature of gravity and what happens to the human body in the vacuum of space. You have seen how easily myth replaces truth when the truth is distant, invisible, impossible to verify with everyday experience, when dramatic fiction becomes more memorable than patient observation. Space is not the place that movies and television have taught you to imagine. It is not a realm of instant explosions and bodies freezing solid in seconds, not a densely packed minefield of tumbling asteroids, not a hunting ground where black holes prowl for victims or where touching a meteorite will burn your hand. These images are dramatic by design, crafted to create tension and spectacle, to keep audiences on the edge of their seats, but they obscure the reality of space, which is simultaneously more mundane in some ways and more profound in others. The truth, as we have discovered together tonight, is this: space is mostly empty, vast beyond human comprehension, with distances so large that even light takes years to cross them. Black holes do not suck like cosmic vacuum cleaners. They simply exist, warping space around them with their gravity in exactly the same way that Earth warps space around itself, only more intensely. You could orbit a black hole just as safely as you orbit any massive object, as long as you maintain your distance and respect the mathematics of orbital mechanics. The asteroid belt, that supposedly treacherous region between Mars and Jupiter, is so sparse that you could fly a spacecraft through it blindfolded and likely never come within thousands of kilometers of a single rock. The asteroids are spread across such enormous volumes of space that they are, for all practical purposes, invisible to each other, solitary wanderers in an ocean of darkness. The sun is not yellow but white, its light only appearing yellow when filtered through Earth's atmosphere, and it does not burn with fire but fuses hydrogen into helium in its core through nuclear processes that will continue steadily for another 5 billion years. Astronauts on the International Space Station are not experiencing zero gravity because they are far from Earth. They are only about 400 kilometers above the surface, still firmly within Earth's gravitational embrace. They float not because gravity has disappeared, but because they are in perpetual free fall, falling around Earth at exactly the right speed to never hit it, held in orbit by the same gravitational force that holds you to your bed right now. If you were exposed to the vacuum of space without a spacesuit, you would not explode like an overfilled balloon, though you would certainly face serious problems. Your skin is strong enough to hold you together, but the absence of air pressure would cause the nitrogen dissolved in your blood to form bubbles, and you would lose consciousness within seconds from lack of oxygen. It would be an unpleasant death, to be certain, but it would not be the dramatic, explosive end that science fiction has taught us to expect. Tonight, as you rest here in the darkness of your room, safe and warm, you are invited to hold the real nature of space in your mind. Not the myths, not the exaggerations, but the complex, nuanced, often counterintuitive reality that scientists have painstakingly discovered through decades of observation, measurement, and careful reasoning. Space is vast, ancient, nearly 14 billion years old, born in the Big Bang and expanding ever since, carrying galaxies away from each other at speeds that increase with distance. Space is governed by laws, gravity, thermodynamics, relativity, quantum mechanics, that shape everything from the orbit of planets to the bending of light around black holes, from the formation of stars to the slow evaporation of black holes over incomprehensible spans of time. These laws are strange, yes, often violating our everyday intuitions about how things should behave, but they are not arbitrary or chaotic. They are reliable, predictable, the same everywhere in the universe, and they create order rather than chaos. But space is also, in a very important sense, separate from you right now. You are not in space. You are on Earth, protected by layers of atmosphere 30 kilometers thick, shielded by a magnetic field that deflects solar wind and cosmic rays, held by gravity that keeps you grounded and keeps the air from escaping into the void. The distance between you and the true vacuum of space is less than 100 kilometers, a distance you could drive in an hour on a good highway, but that thin shell of atmosphere is everything. It is the difference between life and death, between comfort and unimaginable hostility, between a world teeming with life and a barren rock exposed to radiation. As you drift even deeper into rest now, let the myths fall away one by one, like autumn leaves releasing from branches, spiraling down into darkness where they cannot trouble you. Black holes do not hunt for you across the cosmos. They sit quietly in their orbits, patient and still, affecting only those objects that venture too close, and even then only through the impersonal mathematics of gravity. Asteroid belts are not deadly gauntlets but nearly empty regions of space where rocks drift in solitude, separated by distances so vast that collision is more rare than winning a lottery. The sun is not a ball of fire but a fusion reactor, burning not with combustion but with nuclear fire, stable and predictable, warming your planet from a safe distance of 150 million kilometers, a distance that is neither too close nor too far but exactly right for liquid water to exist on Earth's surface. This distance is not an accident but the result of planetary formation processes that sorted the solar system into inner rocky worlds and outer gas giants, with Earth settling into what astronomers call the habitable zone, the Goldilocks region where conditions are just right. Space is not trying to kill you. This is perhaps the most important truth to carry with you into sleep tonight. Space is not malicious, not hunting, not even aware of your existence. It is simply indifferent, a realm governed by physics rather than intention, by mathematics rather than malice. The dangers that exist in space, radiation, vacuum, temperature extremes, micrometeorites, are real but they are not personal. They affect all matter equally, without preference or prejudice, following laws that were written into the fabric of the universe at the moment of its birth. And you are safe here, protected in ways you rarely think about but which are no less real for being invisible. Above your head right now, even if you cannot see it, the atmosphere is doing its patient work, burning up meteors before they reach the ground, scattering blue light to create the daytime sky, trapping heat to keep the surface warm enough for life. The magnetic field generated by Earth's molten core deflects most of the dangerous charged particles that stream constantly from the sun. The ozone layer absorbs ultraviolet radiation that would otherwise sterilize the surface. Earth is not a fragile island barely clinging to existence in a hostile universe. It is a robust, self-regulating system that has supported life for at least 3.5 billion years through ice ages and impact events, through mass extinctions and volcanic eruptions, through changes in the sun's luminosity and shifts in the atmosphere's composition. The planet is resilient in ways that should inspire confidence rather than fear, protected by physics and chemistry and the fortunate accident of being at just the right distance from just the right kind of star. Your breathing has become very slow now, very deep, each breath effortless and automatic, requiring no thought or intention. The day has faded completely into memory, and the night has settled around you like a soft blanket made of darkness and quiet. You do not need to fear space. You do not need to venture into it if you do not wish to. You are allowed to remain here, held by Earth, protected by layers of atmosphere and magnetic fields that you cannot see but which are as real as the pillow beneath your head. The myths told you that space was more dangerous, more chaotic, more immediately threatening than it actually is. They told you that black holes would suck you in from light years away, that asteroid belts were impassable, that you would explode or freeze instantly if exposed to vacuum. But these were exaggerations, dramatic flourishes designed to create excitement rather than convey truth. The real space is dangerous, yes, but in slower, more predictable ways, in ways that can be understood and planned for and mitigated with proper technology and preparation. Astronauts who venture into space do so not recklessly but carefully, protected by spacesuits that recreate Earth's atmosphere in miniature, by spacecraft with thick walls and redundant systems, by mission control teams that monitor every detail and plan for every contingency. They float in the International Space Station not in zero gravity but in free fall, still held by Earth's gravity, still orbiting the planet that gave them birth. And when they return, they land safely, having spent months in an environment that is hostile but manageable, dangerous but navigable. Space exploration is possible because space, for all its strangeness, follows rules that can be learned and applied. The universe is not random chaos but ordered complexity, and that order makes it comprehensible, makes it something we can study and understand and eventually venture into with reasonable confidence. This should be comforting rather than frightening. This knowledge that the universe makes sense, that it can be known, that its dangers can be mapped and avoided. If thoughts continue to arise in your mind, let them drift past like clouds across a dark sky, acknowledged but not grasped, noticed but not pursued. You do not need to solve anything tonight. You do not need to understand everything about space or physics or orbital mechanics. You only need to rest, to let go of the misconceptions that have been with you perhaps for years, to trust that Earth is holding you safely while the cosmos turns overhead, vast and dark and governed by laws that are strange but not arbitrary, complex but not chaotic. So let yourself go now, completely and without reservation. Let the night carry you down into sleep like a river carrying a leaf, gentle and inevitable. Let sleep come not as an escape, but as a return to the natural rhythm of consciousness and rest, the daily cycle that all living things follow, the necessary pause in the constant work of being awake and aware. The myths have been examined tonight, held up to the light of what we actually know, found wanting, and set gently aside. In their place, you carry something more accurate and more comforting. The knowledge that space is not hunting you, that black holes are not cosmic predators, that the universe operates according to rules that can be understood and respected. You carry the knowledge that Earth is protecting you right now, that you are wrapped in atmosphere and held by gravity and warmed by a stable star, that you are safe here in ways both visible and invisible. Thank you for spending this time here tonight, for drifting through the myths with patience and openness, for allowing yourself to see space a little more clearly, a little more accurately. May your dreams tonight be peaceful and free from the exaggerated dangers of science fiction, filled instead with the quiet knowledge that you are on a planet uniquely suited to protect you, held by gravity, surrounded by atmosphere, orbiting safely in the habitable zone of an ordinary star in an ordinary spiral galaxy in a universe that is vast but not malicious, strange but not chaotic. Good night. Sleep well. Earth holds you gently as you rest, and space, for all its vastness and strangeness, remains at a comfortable distance, neither threatening nor concerned with your small, precious, temporary existence. You are safe. You are held. You are allowed to sleep.